Okay, welcome back. This is 10.4. We're working with, sorry, it's 10.5 actually. Jeez. We're working with radicals. Right now we want to worry about multiplying and let's see what else, rationalizing denominators and that'll be about it. So multiplying and then rationalizing denominators. Okay. Camera sort of straight out. Okay, so first we'll deal with the multiplication. And in order to handle multiplication with radical expressions, we may have to do some distribution and some foiling. It's kind of like when you multiply two binomials together, you have to do first outer inner last. So we'll see that occur. We begin with just distributing. So for problem 4, we have radical 3 times 5 minus radical 3. Okay, so we want to distribute. So it'll be radical 3 times 5. And then radical 3 plus radical 3 times negative radical 3. Okay. Rather than putting the 5 behind the radical 3, we always want the constants in front. So this is going to be 5 times radical 3. Instead of putting a little dot in between them, we could just write 5 radical 3. And it's understood that this means 5 times radical 3. Here we have a positive times a negative, so our result will be negative, and then we'll have square root of 3 times square root of 3. You can rewrite that as a square root of 3 times 3. So we'll have 5 radical 3, and then plus a negative, you can rewrite that as minus, and then radical 3 times 3 is the same as radical 9. And then we can simplify radical 9, right? So it'd be 5 radical 3 minus 3. And that'd be it. Usually you're not going to show all these extra little steps. You'll do a lot of it in your head. It's just for the beginning. I want to make sure everybody's, what did he do? I want to explain every little thing, right? As we go along, I'll leave more and more out. So here we have radical 6 times 4 radical 6 minus 3 radical 2. Again, I want to distribute this times this and this times this. So you'll have radical 6 times 4 times radical 6, which you can rewrite as 4 times radical 6 times radical 6. So I'll just automatically put the 4 in front. And then plus radical 6 times negative 3 times radical 2. So I put the 3 in front, and I'm going to, instead of writing plus a negative, I'm just going to cut to the chase and write minus. And we'll have 3 times radical 6 times radical 2. Then we can multiply out the guts here of these radicals. Remember our product rule for radicals. If you have radical A times radical B, that's equivalent to radical A times B, like that. So we can write radical 6 times radical 6 as the square root of 6 times 6, which is 36. And then minus 3, radical 6 times radical 2 is the same as radical 12. Then we want to simplify the radicals. So radical 36 is equivalent to just 6. Minus 3 times radical 12. Well, we need to march out the perfect square. So I factored 12 into 4 times 3. and then I'll be able to take the square root of 4. And so I'll end up with 4 times 6, which is 24, minus 3 times square root of 4 is 2, times radical 3. And then I can go ahead and multiply out 3 times 2, and I get 24 minus 6 radical 3. Okay, let's throw some variables in here. And I believe for the most part in this section, when you deal with variables, you're not going to have to deal with the absolute value issue that we had, where if you're taking the nth root of something raised to the nth power, it's always the, assuming n is even, you'll end up with an absolute value involved. I'm pretty sure we don't have to worry about that here. So, but anyways, let's take a look at something like number 10. Okay, so I have the cube root of x times the cube root of 24x squared minus the cube root of x. Okay, so I'm going to go ahead and distribute. So we'll have the cube root of x times the cube root of 24x squared. Let's go ahead and multiply everything out on the inside and just write the cube root of 24 times x squared. And when you multiply factors with like bases, for instance, if you have a to the 5th times a to the 2nd, you have to add the exponents. Okay, so that would equal a to the 7th. So that's just an example off to the side to remind us how the exponents work. So here when I have x to the 1 times x to the 2, I really end up with x to the 30. And then minus the cube root of x times the cube root of x will give me the cube root of x squared. So x times x will give me x squared. Okay, now so long as the exponent is divisible by 3, I can consider it a perfect cube and pull it out of the cube root. I also want to see if I have any factors that are perfect cubes in 24. And of course, 8 is a perfect cube. So 8 times 3. And then x cubed is a perfect cube. The cube root of x squared, there's nothing I can do with that. So I'll march out cube root of 8 is 2. The cube root of x cubed is just going to be x. So you divide this exponent by this index. 3 divided by 3 is 1, so I have 2x to the 1. And then I have the cube root of 3. Okay, and then minus the cube root of x squared. Okay. Let's keep moving. Let's look at 12. No variables this time, but it's a little different because we have kind of the old FOIL method is going to have to be used. Okay. So you have to go first, outer, inner, last, and 7 times 8 for our first. So we have 50. Why 7 times 8 always difficult for me? 56. And then the outer, 7 times radical 2. And then the inner, 8 times radical 2. And then the last, radical 2 times radical 2. You multiply the insides, right? So it would be plus radical 4. Okay. So I'll have 56 plus 15 radical 2. Okay. And then the square root of 4 is just 2. So how did I get that 15 radical 2? You added this and this together. So to add these, you kind of consider the radical 2 as a variable. So it's like 7 of these plus 8 of these is 15 of those. Okay, finally combine the 56 and the 2. So we'll end up with 58 and then plus 15 radical 2. number 16, we have 7 minus 2 radical 7, and then 5 minus 3 radical 7. Okay, first outer and last, 7 times 5 is 35. The outer, 7 times negative 3 times radical 7. So it'll end up being a negative. So this is a positive term times it. If you want to think of it plus a minus term, so it's a positive times a negative is negative. Okay, so the minus, and then I'll have 7 times 3 times radical 7. So you can multiply the 7 and the 3, and that'll give you 21. And we have the radical 7. And then the inner, so negative times a positive is going to be a negative, so we'll put minus. And then 5 times 2 is 10, and then we have a radical 7 there. I'm sort of going to have to smush this in, apparently. Negative times negative is plus 6, and then we have, so 2 times 3 for the 6, and then radical 7 times radical 7 is radical 49. I'm really smushing that in. Then we can combine some like terms. These guys are like terms. So I have 35 minus 31 radical 7. And then plus 6 times radical 49. Radical 49, square root of 49 is just 7. So I'll have 35 minus 31 radical 7 plus 42. Combine like terms, so 35 plus 42 is 77. Then minus 31 radical 7. Let's look at some more examples then. This one has all radicals in it, so instead of having, like 7 and then a radical here and then a constant with a radical over here, we have radical 5 minus radical 3 times radical 2 minus radical 10. Okay, we'll do FOIL, and when you multiply out radicals, just keep the radical but multiply out the guts. Okay, so we'll have for the first radical 10, then the outer minus radical 50, for the inner radical 6, and then the last negative times negative positive radical 30. Okay, so we want to march out any perfect squares from these guys. I think 50 is divisible by 25. So we can rewrite that as 25 times 2. Radical 6 is kind of stuck. And then 30, there's not going to be any perfect squares in there. So you could try to think maybe 4, no, 9, no, 16, no, and that'd be about it, right? 25, no way. So radical 30 is kind of stuck. So there ain't going to be too many like terms here. Let's see. I have radical 10 minus, I can march out the square root. 25 is 5, so march out a 5 there. And then minus radical 6, and then plus radical 30. Okay. So kind of a bummer when you don't get to simplify, but that you can't wish it to simplify. It is what it is. We're here in math land. Okay. Let's look at 26. I think it's like 26. It's not the same, but okay. A real bad habit some people have is to kind of think, oh, I can distribute this 2 on the outside. You can't do that. You have to FOIL. Okay, so what is this thing? It's a FOIL in disguise, right? So it's really radical 2 plus radical 5 times radical 2 plus radical 5. Okay, and then you do first outer inner last. So radical 2 times radical 2 is radical 2 times 2 is 4. And then the outer, radical 2 times radical 5, 2 times 5 is 10. And then the inner, again, we get radical 10. And then the last, plus radical 25. Okay, square root of 4 is 2. There are 2 radical 10s, so we have 2 radical 10. And finally, square root of 25 is 5. You can add the 5 and the 2 together, you get 7, and then plus 2 radical 10. And this one's like 28, and this is kind of foreshadowing what we need to do later when we rationalize denominators. Okay. So we'll have radical 5 plus 2, and then radical 5 minus 2. And it's a special kind of multiplication that'll get rid of all the square roots. Okay, so first got radical 25, the outer minus 2 radical 5, the inner plus 2 radical 5, and then the last minus 4. Okay. So radical 25 is 5. Square root of 25 is 5. These two guys are additive opposites. So they will add to 0, and you don't have to worry about those, right? They cancel each other out. And then you have minus 4. 5 minus 4 is 1, and that's your answer. So pretty cool. Let's look at one that has some variables. It's similar to that, but it has variables. So 38, I think it's like 38. It's not the same. X minus the 7th root of y to the 5th times 3x plus the 7th root of y to the 5th. Okay, so yeah, this one isn't going to have a cancellation, but let's get rid of that 3 in front of it, and then we'll see it's kind of works like 28. Okay. So again, first outer inner last. Well, is it going to get rid of the roots? I don't know. I actually don't think it will. So yeah, I guess this idea won't always work if you have funny roots. But let's see. Okay, so x times x is x squared. Okay. The outer plus x times the 7th root of y to the 5th. The inner minus x times the 7th root of y to the 5th. So those will cancel out. No problems there, right? Those are additive opposites. It's this last one I'm worried about. Minus the 7th root of y to the 5th times y to the 5th, which will be y to the 10th, because you add the exponents when you multiply out y to the 5th times y to the 5th. Yeah, and then the root isn't going to go away in this case. I mean, you could factor out some of the perfect sevenths. So this would be y minus the 7th root of y to the 7 times y to the 3. Right? And then we could kind of march this guy out because it's a perfect 7th. So I'd have x squared minus y, and then times the 7th root of y cubed. So yeah, unlike number 28 then, where we got rid of the roots, sort of doing this process where all we multiply this times the same thing, but with an opposite sign. See how that worked? I did an opposite sign. It's called a conjugate. Okay. So apparently there's not the same idea of conjugates here as there are here. Okay, we'll look at conjugates in a bit when we're rationalizing denominators. I hope you've seen the rationalizing denominator before. If not, then you kind of disregard everything I'm going on about. Okay. Anyways, we're headed that direction. We need to do a little bit of work first. So what do we care about? We're caring about rationalizing denominators. So sometimes in operations, that you may have to do later on, it's a good idea to get either the radical out of the bottom or the top. And we need tools to be able to do this. First, we'll consider the case when there's just one term in the denominator. And then we'll look at two terms, and that's where you'll see the conjugate come in. Okay. So the one-term case is, let's look at that. So we have 42, the square root of 6 over x. Okay. So the first thing I'm going to do is rewrite it as using the quotient rule for radicals as radical 6 over x, radical x. So my objective is to get this square root out of the denominator. Okay. So in general, what you can do is kind of, you have to be clever sometimes. If in this case, it's pretty easy. You just multiply by the same thing and it will do the job. But you're trying to get rid of the root in any way you can from the denominator. So in this case, in the numerator, you have square root 6x. In the denominator, I have square root x times square root x, which is the same as the square root of x squared. Normally, that would be the absolute value of x. Here, we're presuming that x is positive, so we'll end up with radical 6x all over the square root of x squared will just be x in this case. Okay, so you're trying to set up a case where the radical will kind of simplify away. In this case, it was easy. Let's look at another case, 48, where it's a little bit more complicated, right? So I'll have 10 all over the cube root of 5. Okay, so I want to show you why you can't just multiply by the cube root of 5 and top and bottom. Here, I'll try it. So in the numerator, I'll have 10 cube root 5. In the denominator, I'll have the cube root of 5 times 5, which is 25. Okay, that's a perfect square, though. That's not a perfect cube. In order to get the cube root to go away, we need to have a perfect cube in here. Okay, so this won't work. This idea here won't get rid of the cube root in the denominator. So that's what I'm saying. You have to be a little clever at times. So the best choice then, and you can think of a lot of choices, so it's kind of like a least common denominator thing. You don't want to use something that's huge and unwielding. We want the smallest number that will give us a perfect cube when we multiply it out. So if you multiply by 5 squared, which is 25, it should work. If you do it in the bottom, you have to do it in the top. So I'll end up with 10 cube root of 25 all over the cube root of 125. Okay. Now this thing will simplify, right? So you'd end up with 10 cube root of 25 all over 5. And we got rid of that nasty cube root. One other detail then, of course, if we were the factor 10, it would be 5 times 2. So we'd be able to remove a factor of 5 from top and bottom. I'd end up with 2 cube root 25 all over 1, which is the same as 2 cube root 25. Okay, so if you're looking for kind of a program to follow or something, I give you in your notes, and all you have to do is kind of look there. What you want to do is multiply by something to produce something cubed, right? So if, how do we put that in the words, right? I'm not sure. It's hard to put it in a general sort of way. Let's just keep looking at examples, and hopefully it'll be clear. I think that's probably the best way to explain it. Okay, so 54. We have the cube root of 5 all over y squared. So the first thing, again, I want to do is get this thing split into two parts. And then you got to be clever. You want to multiply by something that inside here is going to be a perfect cube. Okay? So in this case, I'm going to want to multiply by y. Okay, that will give me y cubed, and then I'll be able to take the cube root of that. Right, so if I multiply both top and bottom by the cube root of y, that'll take care of it. Right, so here I'll have the cube root of 5y, and downstairs I'll have the cube root of the y cubed. So y squared times y, you add the exponents. 2 plus 1 is 3. So y cubed. And then you have the situation where you have the nth root of something raised to the nth power. They cancel each other out, and you're just left with y. Let's look at 58. So here I have the cube root of 3 all over xy squared. Okay, so I'm going to split the thing into its numerator and denominator. Okay, so downstairs, I'm going to need, if I have x, I'm going to have to multiply n by x squared to get the x cubed. If I have y squared, I need to multiply n by just another y. Okay, so it's going to be x squared times y, and top and bottom. Okay, so on the top, you'll end up with the cube root of 3x squared y. And the bottom, now we have the cube root of x cubed, y cubed. And then we can simplify the bottom part now. So we have in the numerator the cube root of 3x squared y. And the denominator, just xy. Let's get one more, well, a couple more actually. So here's problem 60. We have x cubed y z all over the fifth root now of x cubed y z. Okay, so this time I need to multiply in by variables to kind of complete the fifth, complete the fifth power or something, I guess. So here you need to multiply in by an x squared. And then for the y, you need a y to the fourth. And then we'll also need a z to the fourth. Okay, so in the numerator, I'm left with x cubed yz, and then the fifth root of x squared y to the fourth z to the fourth. And the denominator, I'll have the fifth root of x to the fifth y to the fifth z to the fifth. And all these are perfect fifths, so you can march them out. And you'll be left with x cubed yz times the fifth root of x squared y to the fourth z to the fourth all over x, y, z. Okay, so we got rid of the root problem. Now we can simplify a little bit the numerator and denominator. So remember, if you have x to, let's say, a to the fifth all over a cubed, you can use the quotient rule to simplify this into a to the 5 minus 3. Right? So you're subtracting exponents when you do division. And in this case, we'll have x to the 3 minus 1, so x squared. And then y over y, that'll just be 1 over 1. And then z over z will just be 1 over 1. So I'm just left with x squared times the 5th root of x squared y to the 4th z to the 4th. Okay, let's look at 68. We have negative square root 150 a cubed all over b to the 5th. Right, so you need to split this. So I have 150 a cubed all over the square root of b to the 5th. Okay, I want to get rid of that square root, so I'm going to multiply in by something that will make this power divisible by 2. Okay, so if I multiply in top and bottom by b, that will do it. Okay, so this guy will be negative square root of 150 a cubed b. And then downstairs, I'll have the square root of b to the 6, okay, which is a perfect square. So I'm also going to start thinking about pulling perfect squares out of the numerator. 150 is the same as 25 times 6. And then a cubed is the same as a squared times a. And then we have a b. Okay? In other words, I can factor out this and this. Downstairs, the square root of b to the 6 just divides 6 by 2, and you get b cubed. And then the numerator, you can march out the square root of 25 is 5, the square root of a squared is a, and then on the inside, you're left with 6ab. And then, of course, that's all over b cubed. Okay. Okay, I think that's probably as bad as they'll get. Let's now turn our attention to conjugates. And in particular, you use these when you have two terms in the denominator as opposed to just one factor up here. Okay, and you'll use this thing called the conjugate. Okay. So again, we've seen the conjugate before, and I started talking about it a little bit in this example here. So if you have radical 5 plus 2, its conjugate, to get the conjugate, all you have to do is change the sign to its opposite. Okay? And when you get that, it'll get rid of the root. Okay? So that's what we're after in this section. Let's take a look at what we have. So 76. I have 15 all over the square root of 16 plus 1. So to get rid of the square root here, you need to multiply top and bottom by the conjugate. So the conjugate is just the same thing, but with an opposite sign. So square root of 16 minus 1. Square root of 16 minus 1. So in order to pull this off, I'm going to have to do a distribution in the numerator. Okay, so that'll look like 15 square root 16 minus 15. In the denominator, you have to FOIL. Okay, so it should be just square root 6, but I went big apparently. So what the heck is 16 squared? I don't have my calculator here. 6, 3, 6, 7, 8, 9, and 16, 6, 256. So we first gives us square root 256. The outer minus square root 16. The inner plus square root 16. And then the last minus 1. So I have 15 square root 16 minus 15 all over. Negative 16 and positive 16, they're additive opposites, so they cancel each other. The square root of 256 is just 16. And then minus 1. So I have 15 square root 16 minus 15 all over 15. And then I think we can simplify a little. So I'm going to have to refactor out the 15. I distributed it early. So I have square root 16 minus 1. Oh, and lo and behold, I can remove the 15, and I'm just left with square root 16 minus 1. Just 2 more examples, and that'll be it for this section. So we have 80, 12 all over square root 7 plus square root 3. So you just take the opposite sign. Okay. Up here, instead of distributing, let's just keep it as it is this time, right? So it's 12 times square root of 7 minus square root of 3. In the denominator, I'll have square root 49. The outer minus square root 21. The inner plus square root 21. And then the last minus square root 9. So that'll be 12 times the square root of 7 minus square root of 3. Those 2 middle guys are the same, so they go away. And then we have square root of 49 is just 7, minus square root of 9 is just 3. Okay. Now we can simplify a little bit. It's already kind of factored. 12 over 4 is the same as 3 over 1. So we'll be left with 3 times radical 7 minus radical 3. And you can distribute that if you want. That answer, though, is fine for me. Let's look at one last one. We'll call it quits for the day. Radical 11 minus radical 5 all over radical 11 plus radical 5. Okay. So this time I want to multiply top and bottom by radical 11 minus radical 5. Okay. And the numerator, first, outer, and last, we'll have square root 121, so end up just being 11. Okay. And then the outer, minus square root 55. The inner, again, minus square root 55. And then the last, plus square root 25. Downstairs, you have almost the same thing, except the signs are a bit different, right? So square root 121 plus, or rather, the outer would be minus square root 55, and then the inner plus square root 55. and then the last minus square root 25. We want to start simplifying. So square root of 121 is 11. And then we have 1, 2, minus 2 square root 55. And then plus radical 25 is the same as 5. All over square root of 121 is 11. And then these are additive opposites, so they go away. And then minus radical 25, which is 5. 11 plus 5 is 16. And then minus 2 radical 55. And then that's all over 6. And we should be able to simplify a little bit. So I want to factor these guys. I can pull a 2 out of the numerator and have 8 minus radical 55. And the denominator, 6 is the same as 2 times 3. And so I can remove the 2's. And I'm just left with 8 minus radical 55 all over 3. And that'll do it. Okay, thanks for watching.